Most students try to memorize molecular geometries like they're random facts, but the truth is, molecular geometry is actually incredibly logical once you can visualize electron domains around the central atom. In this video, I'm going to show you how to see electron domains in 3D, how each number creates a specific geometry, and why molecules naturally arrange themselves this way. So the core of the VSEPR theory is that electron domains arrange themselves in a way to minimize electrostatic repulsion. But what are electron domains? Electron domains are caused by a high electron density around a central atom. And what would cause high electron densities? Electrons. So if we have a central atom A, and it has lone pairs or non-bonding electrons. These lone pairs contribute to the electron density around the central atom and therefore would be an electron domain around the central atom. If my atom is bonded to another atom, there's an electron pair in the bond, and that electron is causing electron density and therefore is also an electron domain. Now it doesn't matter if it's a single bond or a double bond or a triple bond, because in those bonds are electrons that's causing a high electron density around the central atom and would be an electron domain. So this is key. Single bonds, double bonds, and triple bonds all occupy one electron domain. So a single bond, one domain. It's a double bond, it's one domain. It's a triple bond, it's one domain. So a molecule that looks like this, where it's two double bonds, that's one domain, that's one domain. So it doesn't matter how many bonds there are between atom A and B, it still counts as one electron domain. Whether it's a double, triple, single, it's one electron domain. Now that we know what electron domains are, it's much easier to count them. So I'll use the example of ammonia. I can count the domains around the central atom. So there's one domain there, one domain there, one domain there, and one domain there. That's 4 domains. 1, 2, 3, 4. Another example is carbon dioxide, and I'll count the domains around my central atom. That's 1 and that's 2. There are 2 domains around my central atom. So that's the first step. We should be able to identify what electron domains consist of, either bonding electrons or non-bonding electrons. And then the next step would just be to count them out. How many electron domains do we see? The next part is where it gets a little bit more complicated, the visualizing what the electron domains look like in 3D space. So to understand what they will look like in space, so it's important to think about what we know about electrons. Like electrons repel each other. If we have two areas of high electron densities, they're going to repel each other. There's that electrostatic repulsion. So let's say there's an electron domain, here's an electron domain, and they are going to repel each other. Now, if it was just electron domains not attached to anything, they would not want to be close to each other. But if we have to connect them to a single point, like the central atom, they would be forced to be close to each other. But they would orient themselves in a way that they minimize the electrostatic repulsion, so they will want to be as far away from each other as possible. Let's say we have a balloon and it's tied to that point. That single balloon can do what it wants. It can be here, there, nothing's going to affect it. Now, if I was to add a second balloon and I want to force it right next to that, I would have to really push on these two balloons to be so close to each other, because they will exert forces on each other, and if you can picture balloons, they would not naturally just be squashed together on one side. They would orient themselves in such a way that they are the furthest away from each other. Now they both have free space around them. They are the furthest away from each other. And electron domains are just like these balloons. They don't want to be close to each other. They would rather be as far away from all other things as possible. So let's say I add a third balloon on that side. It would kind of push the blue one and the purple one away from it, because it wants to be as far away from those two as possible. Therefore, the blue balloon would orientate itself so that it's away, and then the 3 balloons would be connected like that. They would be equally away from either balloon on either side. Now when I add a 4th balloon, they can't all be in the same plane. As you can see, it will be way too squished. So it kind of orientates itself in such a way that they are 2 opposite each other, up and down, and side to side. Something like this, where there's one balloon, and then there's one balloon, there's one balloon. And this is what electron domains are doing. They are orientating themselves in such a way that they are far away from any other domain as possible. And that's why we have to know how much domains we have in total, and then we can predict how they would orientate themselves. Now that we know the VSEPR model is all about how these electron domains orientate themselves in space, and we know what electron domains are, we can easily predict what the electron domain geometry will be. If I have a molecule A, B, 2, and it's bonded with double bonds, where A is the central atom and B is the terminal atoms, I can see that I have two electron domains. And the electron domain geometry will be linear. If you can remember the balloons, they would prefer to orientate like that. As soon as we have two electron domains, it's a linear electron geometry, and then its molecular shape is also linear. And that's because all linear electron domain geometries are linear in molecular shape. There's nothing else affecting it. It gets more complicated when we move to more domains. If you can think of the balloons, the more balloons we added, the more complex it got in how they orientated themselves. It's the same with molecules around a central atom. Our next example is AB3. So that means we have a central atom bonded to three terminal atoms. If we count how many domains we have 1, 2, 3 domains. And the electron domain geometry, I will abbreviate, is trigonal planar. That's not our molecular geometry, that's our electron domain geometry. So electron domain geometry is how our electron domains are arranging themselves in space. If you want the molecular geometry, we have to look a little deeper in each electron domain geometry. So that's the key distinction. You have the big category, electron domain geometry, and then in that geometries, there are smaller categories of molecular shapes, and that we'll discuss in another video. This is just about counting domains and figuring out the names of those domains. Let's say we have AB4. Now we have another bond. That's 1, that's 2, that's 3, that's 4. 4 electron domains. Our electron domain geometry is tetrahedral. It doesn't necessarily mean our molecular shape is tetrahedral. Again, we have our electron domain geometry, and in that we have our molecular geometry. So we first have to identify our electron domain geometry, and then we're able to get our molecular geometry. That's an important distinction. Our electron domain geometry, we are looking at our domains around it. When we look at our molecular geometry, we look at what our bonding electrons are doing, and that's a different type of geometry. So our electron domain geometry is not our molecular geometry. Let's say we have AB5. I add a fifth bond to my central atom. I'll count up my electron domains. 1, 2, 3, 4, 5. 5 electron domains. Our electron domain geometry is trigonal bipyramidal. If you've seen the shorts on the hack, then you'll know an easy way to remember that 5 domains is trigonal bipyramidal is to look at tri and bi. So most of us can remember that tri is 3 and bi is 2, and this gives us 5 electron domains because of tri-bi. So if you're trying to remember what is the geometry of 5 electron domains, think back, there was 2 words that has to add up to 5. So 5 domains is tri-bi, trigonal bipyramidal. Now let's say we have AB6. This is our central atom A bonded to 6 terminal atoms. I'm going to count how many electron domains are around my central atom. 1, 2, 3, 4, 5. 6 electron domains. That means our electron domain geometry is octahedral. Now, this is confusing to a lot of students because we always associate oct with 8. We think of an octahedral shape. It got its name because there are 8 faces, but our octahedral also has 6 vertices, right? And if we think of vertices as kind of the points where the 2 lines connect. So here's our central atom. It kind of has 6 points of connection, and that's where the octahedral shape comes about. So 6 domains, our electron domain geometry is octahedral. It's not 8 domains, it is 6. So that was our electron domain geometries. So to summarize, we have 2 domains. That's a linear electron domain geometry, and it looks like this. We can have 3 domains, and our electron domain geometry is trigonal planar, and it looks like this. We can have 4 domains, and that's tetrahedral, and it looks like this. We can have 5 domains, and that's trigonal bipyramidal, and it looks like this. We can have 6 domains, and that's octahedral, and it can look like this. So you can see each number of domains we have corresponds to a specific electron domain geometry. 2 is always linear. 3 is always trigonal planar. 4 is always tetrahedral. 5 is always trigonal bipyramidal. And 6 is always octahedral. Again, I want to emphasize that this is electron domain geometries. This is not our molecular geometry. This is our electron domain. So if you think about it, we have our electron domain geometry kind of as this big umbrella. And then in this umbrella, we have different molecular geometries. So our molecular geometries is in our umbrella of electron domain geometries. This summary of names is just for the electron domain geometries. So now that we know our specific domains have specific geometry names, I'm also going to show you what they look like in 2D so that you can always remember and then from there work out molecular geometries. So our linear looks like that, trigonal planar looks like that, tetrahedral looks like that, trigonal bipyramidal looks like that, octahedral looks like that. So that's our electron domain. Now that we can visually see what each electron domain geometry looks like, we can use this to predict our molecular shapes, which becomes a lot more easier once you understand what the electron domain geometry looks like, because then you're able to place in your bonds, your lone pairs, and all of that, and then deduce the shape from that. But you'll see in another video how easy it is to predict the shapes if we know our electron domain geometry. So we don't have to memorize every single molecular shape. We just have to memorize what our electron domain geometries are. And from there, we can always accurately deduce what our shape would be. And then the more you practice, the more you'll just remember the molecular shapes as well. But don't try and force yourself to memorize electron domains and then all the molecular shapes possible. That's confusing when you're in the exam and you need to recall based on the shape you've just drawn. So feel free to screenshot this. And if you'd like to see a video on how to accurately predict molecular shapes just by knowing our electron domain geometries, click on the video on the screen. If you'd like a refresher on how to draw Lewis structures, you can go to the video listed in the description. Thank you.